means that all you ever see.
What?
What?
That alone. That looks like it's something. Oh my god.
Why is that true? It's so funny.
Because she should have like.
I know.
It's just funny.
Why is that?
It's just really.
It's a true.
Because they like actually look like. Yeah. Like there's like.
Wait, do you think it was mean? I wasn't trying to be mean.
It's better than what Porter's now.
Do you think I was being mean?
After.
Would your sister think I was being mean?
Not for this.
Should be offended. So, I didn't say anything about offended. I'm offended.
It's just because I'm more about.
But your head is shaped. That's a true statement. What are you like talking about? I feel like I offended someone. What do you want? No, I don't.
I think you do.
We're recording right now.
Oh, I can't say it.
Okay.
That's great.
Yes.
I don't think you're allowed to laugh at it.
My back's bothering me, and I'm just trying something different. See,
I'm writing it down for you. You can't laugh at it. Yeah, don't laugh because
I have a pretty good idea. I think.
I don't think you know what you're saying.
Oh, really?
Pretty good idea. She came back after Christmas.
When did she ship her out? Like over Christmas?
I think so.
Are you serious?
Dave's gonna be so confused, like, what's going on?
What did she say?
Yeah, why is it that so low?
I know.
I think she thought it was funny.
Okay.
Also, yeah, why is your nose low?
He asked that like 1 minute ago, and I answered, and nobody paid attention. Well, maybe you don't deserve to answer then.
His back has been bothering me. Shake my head now.
Wait, why is
I heard it.
That fake tall chair's been bothering my back, so I'm just trying something different to see if this puts me in a different position or something. Yeah, I don't know. Okay. So we're doing a T-test. Do you want me to use the sheet? Doesn't matter. I'm gonna do. Yeah, I didn't really say what I was doing. I guess I was distracted by the other conversation. I'm gonna do the template outline. I'm just using a regular sheet of paper to do it. Does that matter? Okay. So the first thing you do is say mu equals true population mean whatever. True population mean ACT score, true population mean height, or true population mean number of siblings. We've done that before, and then you're gonna have HO. And HO is always zero. This is it's called a null. The zero, that's the starting point. That's and you're kind of on top. This is like your position, unless you can prove otherwise. This is where I'm going to stay. Like you're going to have to really convince me that this is not true, or I'm going to think it is. So the burden is on proving that it's not true. If we can't prove it's not true, then we're like, okay, maybe it's true. So HO is always going to be mu equals some number. It has to be equal. So that's like the initial claim. I think there's an average of 10 M&Ms in a little pack. I think the average ACT score is 12. Why is it 12? 12 is really bad. Whatever, you know what I'm saying. And then HA is the alternative hypothesis, which we think there's something going on that's different. And I might think mu is greater than that. I might think mu is less than that, or I might think mu is not equal to that. And this is my stance, that the h sub 0 is my stance, unless we can mathematically prove that there's enough evidence to support one of these. I'm going to just default back and be like, well, I think this is still true. Yeah.
So like are the two numbers like they're going?
They're the same. So like, I don't know how you want me to write that. So it's the same number. Yeah, so if I think the average ACT score is 12, this would be greater than 12, less than 12, not equal to 12. So same number. Then you got your conditions. So I'll just put same number. Conditions we've done before. That's the RIT, right? So randomness. It's usually stated. Independence. There's two ways we can show independence. Shram, give me one of them. So our sample, our little n, is less than 10% of the population. I don't know, what's the next one? What's the other independence one? I was going to call it someone, but then I feel bad calling it people. I don't want to put the ones that, but I also want to like involve it. It's tough to talk about it. No, what was the other one?
Each like thing in the sample.
Yeah, so just say like assume each whatever. And then T is for T distribution. And there's three possibilities here. You just need one of them, but there's three things. So the first thing you would look for is the population normal? And then the second thing would be, okay, if the population is not normal, we're still okay if we have a large sample size. So you need n to be greater than or equal to 30. And then if we don't have a normal population, and we don't have a large sample, we're still okay if our small sample is approximately normal. So like that box right there is nothing new, right? So that's kind of nice because you know that already. Good so far? Okay. Let's get a formula sheet. Or let me share one. If you have one. So this right, you don't have to get out, I guess. I mean, you can just look at it if you want. That right there is what I want to look at. So these are like the whole second half of the year is confidence intervals and tests. So when we did confidence intervals, we went, this is the first thing we wrote down at every single problem we did, right, for confidence intervals. This is the first thing we write down for everything on tests. So, and you don't even have to, yeah, you should. So we're going to write standardized test statistic equals, we're going to write all that. That's like so there's the formula, letters, numbers, answer. Right, so we're kind of doing that same deal. So you're going to write that every time. But if you forget it, it's on your formula sheet, which is nice. So standardized test statistic equals statistic minus parameter over standard deviation of statistic, and then the formula sheet also has a list of all of those standard deviations. So then we can look at each of those things individually and figure out what goes where. So your standardized test statistic is T or Z. If we're doing a t-test, we're working with means, it's T. So T equals statistic. Is a statistic the number that comes from the sample or from the population? Statistic is from the sample, SS, and then, so a sample, and we're dealing with means. So how do I notate sample mean? X bar. A parameter is a number that comes from the population. We're dealing with means. How do I represent population mean? Mu. Standard deviation of the statistic. So this is on your formula sheet. Remember, we don't ever worry about these. But if you forget, I think you guys probably know it, but if you forget standard deviation of the statistic, I'm working with sample means. Boom, right there. So standard deviation divided by the square root of that. So that goes on the bottom. And then I think the easiest way to work organizing this is a little different than the confidence interval. I'm going to work like a cross, because I want to save space below, because I have to make a drawing in this one. So like across wise, I'm gonna go, okay, next I'm gonna plug in the numbers. So this is like this is in words and then symbols, numbers. And then I'll get a t-value. So we have trying to organize. There's three situations because the way it works, if we're doing a greater than or a less than or a not equal, are all different. Alright, so you're not going to do all three of the things I'm showing you right now, but like write them all down in your template, so you have them. So let's say that the original thing was mu is less than. I'll try to split it up. If mu is less than, the next thing you're going to do is TCDF. So that's like normal CDF. It's in the same menu. And because it's less than, I'm going to want, so that T, you're going to get a T value. And if it's less than, the T value is going to be over here. It's going to be below your mean because we want to know if it's less than. So you might get like T equals -2. What does normal CDF find? Like if I did normal CDF, I'm not asking that well. Let me just say it. If I do TCD, I want to find the size of this area. So I want to find like the shaded region from that down. And I'm looking at that down because this is a less than. If it was greater than, I'd be looking up. And if it's not equal to, you look at both. So because I want to look at that spot and below, I would go TCDF -999, comma the T value that I just got, comma degrees of freedom. So that's this case here. If it is mu is greater than, now your T value, so this is your mean, your T value will be up there, it might be like 1.8 or something, and I want to know this shaded part. So what would I do? TCDF what? That, and then 99999, and then degrees of freedom, right? So it depends on the order, or the order depends on whether we're greater than or less than, or whatever. So this would be T, comma 999, comma degrees of freedom. And then if its mu is not equal to, this one you do both. So if T, so this is your mu. If T came out to like, let's say T came out to 2. Well, what you would look at then is we're going to not only look at if T equals 2, but we're also going to look at T equals -2. So you're looking at both sides. So what you do is one of those, whichever one you have. Like if you have -2, find this part and then do what with it? Because you need to include that other part also. Okay, double it is what I was thinking. Like these are going to be the same, right? So if you just found one of them, then you just double it. If you want to use the T equals 2 and find this part up here, go 2, comma 99999, and then double. the not equals, the less than, I'm just concerned, is it lower than what I think? The greater than, I'm just concerned about, is it bigger than what I think? The not equal to, I'm concerned about, is it bigger or smaller than what I think? So I need both.
Is it always going to be like even like that, like -2 and +2,
or negative 1.8, positive 1.8, or whatever. It'll be the same number. It'll be symmetric. So you're gonna do one of those two and double, because you need both parts. So how do I write that? So 2 times TCDF -999, comma T, comma degrees of freedom, or 2 times T, comma 9999, comma degrees of freedom. What's up?
You're right.
I put 2 times.
Oh.
Where I come from, that's doubling.
That's not right.
No, no.
You have to show the degrees of freedom on this.
So you're gonna put like, so over here, yeah, let's go. Okay, degrees of freedom equals whatever, and then in this file, you'll just put like 9 or 12 or the number of that.
But you have to.
At some point, you need to tell them what degrees of freedom are. You could do it by writing this, and then just right below, like you would write, you might go TCDF -999, comma 8, or no, comma 2, comma 11, and then just right below it go DF. And that counts. Like if that's how you want to label it, you gotta remember that works. Any other questions? Okay. Then, what those things find in each case is what's called your p-value. So you want to put equals p-value. In all those spots. Then we're going to have a drawing. Then we're going to have our conclusion. Alright, let's try this. We're going to draw, the drawings are different depending on which one you have. So if you have the less than, you would draw this little normal curve guy. You put your mu on there. So whatever the number was, you put, so average ACT score is 12. You put 12 there. Then you go over here. Put X bar. So this is our sample data. And so we know our sample data is lower than our mean. The question is it like significantly lower than our mean? Is it like an outlier? Is it that far below that I'm going to be like, okay, yeah, something weird is going on. On top of that bar, you put the T score that you just got. So the one from like way up there. And then this little shaded part over here is your p-value. And I think this will make a lot more sense when we actually do one, but you can use an arrow and point at it. You can write on it. You don't have to write. Alright, if I have, so this one you can probably do on your own, it's kind of similar. Now we're looking, is our data above what they claim? So you're going to be on the upper side, so you'll have X bar there, T equals there, and then this shaded area is your p-value. Then over here, you would have to look at both. So you put the mu in the middle, and you'd have a T equals and an X bar on both sides. And the p-value gets a little goofy there. Well, I don't like it, but I feel like we're going too far down that road right now. So we'll just leave that there for now. to be given to you. If it is not given to you, it defaults to 0.05. Then, you have two options for your conclusion. What the alpha is like the cutoff point. So, if our p-value is smaller than the alpha, then our sample is far enough away from the mean that we're going to say the mean is a lie. If our p-value is right. So, first option is p-value less than alpha. That would mean we reject H0. That means there is sufficient evidence to support HA. So make sure you realize that's an O, that's an A. So I'd be rejecting the initial claim because I think the alternative claim is bad. That's what this means. And then you would say we do believe, and then you put HA is true in context. Or your p-value is greater than alpha. In that case, we fail to reject H0. We're doing that because there is not sufficient evidence to support HA. So I'm not rejecting H0. You didn't convince me that there's something else going on. So there's not enough evidence to support this other idea that you were trying to say. We do not believe HA is true. And put context. So the reason I was trying to sneak up on it, part by part until we got to the big picture, is because this is a lot. I mean, that's a lot of stuff I just threw at you. But I'm in support of this rails. I imagine you're confused as heck right now. But let's do a couple. Let's see where we're at then. Are there any questions I can answer right now?
Yes.
Or could you not even ask a question at this point?
Yeah.
Did you write it down?
Yes.
Alright, let's do an example. So, sorry. I never, that's what I was.
Oh, wow. So
Those are the only two options. What if what? What if they're equal? Never seen that come up. Just hope it's not. Yeah. I think technically it needs to be less than to reject, but I don't think that you have to worry about it. So write that down on the back of, back one of the templates, then we'll do the problem in front. Or you could just go to the front and put mu is 1100, x bar is 1000, n is 35, standard deviation 100. And you don't really need to write down the words, Discussing is getting harder, like you said.
Yeah. Quarter one sucked. Yeah.
Seriously?
I had a hard time. It's just getting used to it. I mean, I feel like quarter one felt the easiest for me, but then when it came to the tests, I still didn't do it. I knew
It's hard
everything,
for me
but I still
'cause
couldn't get it.
I don't know you guys yet. Quarter one, so it's hard for me to tell what.
It's March.
No, in quarter one, I'm saying.
Oh, yeah.
So it's hard for me to tell, what you know, what you don't, because I don't know how you know what I mean?
Nothing. You know nothing.
No, I think I know you know. Some of you I wish I did.
I told you this by now. Our David, freshman year, and then Forrest, sophomore year.
Choral festival.
It's very quiet. Uh-oh. It's gone.
Everybody need it still?
Yeah.
How long does that take?
I'm sorry, you distracted us with your quarter one. Yeah. So
I didn't say
Lower brought it up. Oh, I got distracted. Anybody want to go buy me a 5-hour energy? Do you know what's better now, though?
I would think so. Yeah.
No, it's funny that you still don't know us. I was like, David's the one who doesn't know my first name. Your name?
Wish I didn't know your first name, but I do.
One of these days, evidence has awesome. You guys. No. So what's your name? What would you do if somebody just walked in the room and just said your first name? People somebody just get hey Rod.
So someone's just gonna walk in my room and say, Jeff?
No.
Walk out?
What's up, Jeff?
That's what you're saying?
What would you do if someone walked in and was like, Jeff, give me the paper, please? You'd be like,
Is it a teacher or a student?
a student.
Rod is his last.
If David walked in here and was like, hey Jeff, do you have the work? I'm going to see you. I call him Austin.
Are we good?
Yeah.
Go into Schleich class. What's up, Jamie?
I would not go. Call or no, do it to Pack.
Walks in his
So Christopher.
Yeah. Hello, Christopher. Good morning.
She's like, hey. Rod's like, hi.
Okay.
He walked into his class. Hey Craig, which is his
He doesn't respond to Soupy.
You know what he said? He goes, I don't respond to my slave name. I was like, you can't say that.
I was at his slave name. I heard that.
Oh, it's recording. Just kidding.
No one's gonna watch it. It's fine.
No one watches that either.
I actually do when I was
Do
gone.
you? Alright, good.
I'm gonna have to.
I
It's like, look,
I just asked what you did this class and I'm on and I'll watch the videos. Hey,
I wrote another
I
recording.
look at the notes, but I don't. That might be my phone. You always send them to me. I never rewrite them.
So we're trying to make a statement, a conclusion about the population, right? So just like before, the opening statement and the closing statement are about mu, they're about the population, because that's what we're trying to make a guess about. The stuff in the middle is about X bar, because that's the data that we had. So HO is, okay, the school claims that, what did I put, 1,200? 1,100? Mu is 1,100. I think they're trying to make themselves sound better than they actually did. I think mu is less than that, so I think it's less than 1,100. Now keep in mind, there's wiggle room. There's a margin for error. There's random variation. Not every sample of 30 would result in the same thing, right? So I took a sample of 30 people, I think I said? 35? Whatever, okay. So 35 people, those 35 people had an average of 1,000. Well, is 1,000 less than 1,100? Absolutely. But is that enough to convince me that the whole group average is different or not? That's the question. So, I see you. I'm on a roll now. So, like if I take multiple samples of 35, this is an important question. Would they all come out the same? They would be different, right? So I might have picked the 35 dumbest kids in the school just now. I might have picked the 35 smartest. I have no idea. So you have to allow for like this random variation, and then if it gets past the point of random variation, which is what the math will help us do, that's when I'm like, okay, wait, I don't believe it. Yes.
So is it going to be fairly obvious, like whether you, like, is it going to be a big enough difference to where it's very obvious whether you should believe it or not?
Like just looking at the question? No. Because like a lot of things matter. The standard deviation matters, the size of your sample matters, how far away you are from the mean matters. And so that's what all the calculations at the end will be obvious, because we'll do the math.
Yeah.
Alright. So randomness. I hope I stated that. I can't even remember. Did I say it was random? Alright, randomness stated. Independence, be careful on this one. Can I use the n is less than 10% of the population? 35 would mean I need 350 people at this school who have taken the SAT. I don't think we have that. So then you got to go back to the other one. So assume each student is independent. In like 3 weeks, we'll have 350. And then T distribution. So what is it about this one that makes that okay? I have a large enough sample, right? It didn't say the population was normal, but I have a large sample. 35 is greater than or equal to 30. Alright, now you're writing down the same words you would write on any test. So standardized test statistic. Equals statistic minus parameter over standard deviation of statistic. Caught up, you good? Alright, what's the test statistic? T. What's the statistic when we're dealing with means? Bar. Population we're dealing with means with parameter. Mu, and then this is on your formula sheet. This is that standard deviation divided by the square root of n. And then I'm going to put those numbers in. So, I think I said 1,000. Hertz bar. 1,100 for mu. Standard deviation was 100. And divided by the square root of 35. So now we gotta figure that out. Well, yeah, that's pretty good. I got negative 5.91. 916. You're asking me how to type, where to go to type what? 1,000 minus 1,100 into your calculator? Yeah, we're gonna get there eventually, but right now we're just doing like, just type in the math. How do I subtract? Before I forget, I should write down the degrees of freedom. What are they? 34? Did you say negative? Okay. So then what I need to find is my p-value. Which we haven't even really talked a ton about what that is. I get that, but we're going with the big picture of the narrow approach here. So we're going to do TCDF. And this is a less than spread situation. So this t-value is way to the left of the mean, isn't it? This is like a z-score. This is like how many standard deviations, basically. So we're almost 6 full standard deviations below the mean, which at this point, now it's kind of obvious, to me at least, this is really far away. If it's really far away, what does that make us think about their claim? It's false. We're probably going to reject it, because this is like really extreme down the graph from the mean. So TCDF, but I want to know the part of the graph that is lower than this. And why do I want to know the part that's lower than this? Well, what earlier? What tells me that I'm going to look at this number and lower? Yes, it's the less than. It's that less than right there. This is basically pointing like which direction we're going. So I need to know what's below that. So negative 999, comma negative 5.916, comma 34. And if you didn't label degrees of freedom over there, you could just go down here now and say, okay, DF, right there. So then go, okay, TCDF is in, it's like in the same menu as normal CDF, or inverse norm, or inverse T, any of those. So I got basically 0. I got 5.5 e to the negative 7, which is pretty much 0. So I'm going to say approximately 0. And that is what's called your p-value. Yes. So I want to talk for a second about what the p-value means. The definition of p-value is, well, don't write it down like we're just talking right now. We'll write it down and practice it more later. If this claim is actually true, there is a certain probability that I'll grab 35 random students and their average will come out to 1,000, and that just happened because maybe I just picked like the lower end students. There's a certain probability that happened, right? That is the probability that that happened. So in this case, there's basically a 0 probability that this is due to random chance. So we're not this far away from the mean out of random chance. What that tells us is that the mean is wrong. So that's kind of the thought process of this. This is not the perfect way to think about it, but this is very similar to saying this is the probability that their claim is accurate. It's not perfect, but it'll get you in the ballpark. So if there's a 0 probability their claim is accurate, what does that tell you? Are we going to reject it or fail to reject it? Probably going to reject it. So that is our p-value. Now we need to, and we'll practice that more for sure. Now we need to draw it. So the mu equals 1100 goes in the middle. And then over here, I'm going to put, this is kind of representing my data. So my x bar was 1,000. My t was negative 5.916. And then this shaded part represents my p-value, which I know the p-value is 0, but I have to shade something. And so, let's write down alpha too before we forget. So alpha is 0.05. So the alpha is the cutoff point. Again, I'm trying to teach a bunch of crap today, and I get that. We'll revisit it all. Somewhere around here, there's a spot where the amount of area below that spot comes out to exactly 0.05. So there's 5% of the data below some spot here. That's our alpha. That's the cutoff point. If we are further from the mean than that point, that's where we say, okay, that's too far. Now I reject. So what we're doing is comparing the size of our p-value to the size of that alpha. So below, from here, all the way down, would be 0.05. Our p-value is past that, right? Like we're on the other side of that. Our shaded area is much smaller than the 0.05. That tells us we're further into the tail. That tells us we're going to reject. So that's the point of the alpha. It gives you that, like, there's no gray area this way. You can say, like, yes, we're too far. No, we're not. Yeah.
Does your bell curve have to be accurate whatsoever? Like, where you put it?
Not really, because like mine's not right here.
Okay.
It just has to. I mean, you should have like the correct side of the
General
mean,
idea.
but yeah, no, it doesn't have to be to scale or anything. Okay. So then at the end, if you look at your template, am I going to be doing option 1 or option 2? Doing option 1, right? So p-value is less than alpha. That means we reject h naught. There is sufficient evidence for HA. We do believe mu is less than 1100. And on the template sheet, I said you have to have context in your answer. It doesn't really look like I put context in my answer, but did I? I did, because that mu has context like built inside of it, right? And that's a complete t-test. Yes.
Do you have to include like p-values? Like when you're
That is possibly the most important thing on the whole thing, actually. So yeah, because that's the comparison. That's like how we tell. I mean, I understand you don't understand all of this, but like any questions that you feel like you could ask at this point, or I think I can help with right now. Yeah.
For the p-value is less than alpha in the, like the conclusion section, if you put the numbers in, would that be fine with your other house?
You could put it in addition to this, not instead.
Okay.
So you know what I mean?
Yeah.
Okay. Any other thoughts, questions, concerns, comments at this point? Yeah, so yeah, we'll practice that for sure. So when you're done, I'm not going to give you homework. We'll just keep going tomorrow.